Google Colab, short for Google Colaboratory, is a cloud-based platform that allows users to write and execute Python code directly in a web browser. It provides a pre-configured environment for data analysis and machine learning without requiring any local software installation. In this project, Colab is used to load satellite data, process NumPy arrays, train machine learning models, and visualize classification results. It is particularly useful for reproducible workflows and for working with large datasets in Earth observation applications. Before starting the practical demonstration, I will first explain the objective of today's task. According to the Introduction to AI and Machine Learning, a typical machine learning project follows a structured processing chain, including problem definition, data preparation, model training, and evaluation. In this exercise, the problem is defined as the discrimination between sea ice and leads using satellite imagery. This is a binary classification task, where each sample is labeled as either sea ice or lead, based on manually created ground truth data. The purpose of this task is not to build a highly optimized model, but to understand how machine learning can be applied to Earth observation data by following the complete workflow. First, locate the corresponding Jupyter notebook for this week on the Moodle page. Click the Google Drive hyperlink below the title to access the data we need for this week. Once inside, download and extract the entire Week 2 folder to your drive. Then, right-click and select Colab as the opening tool. In Colab, in the upper right corner, link the code. Then, run the code in each section to operate normally. Next, I need to modify the path here. I need to move it to the location of the Week 2 folder that I just downloaded under my drive. This step is very simple. Just execute the code in the first line to connect your Colab to my drive. Then you will see a new file called My Drive in the file on the right. Then you just need to find the file you need, right-click it, and you will see a copy path. Just click on this location to copy the path of the file. Then you just need to copy and paste the corresponding location in the original code. Now let's officially begin our task for today. We'll start by handling the changes to the path code and the save location, and complete all the preparatory work. Now I will start running the code to construct the dataset that will be used for machine learning classification. First, I visualize the selected region of interest from the original OLCI image by combining several spectral bands into an RGB-style image. This allows me to visually confirm that the selected region corresponds to the same physical features as the binary mask created in Iris. I then plot the binary mask itself, where the two classes represent sea ice and leads, and this step is important to ensure that the labels are correctly aligned with the image data. After that, I check the shape of the data arrays and confirm that the region of interest has spatial dimensions of 300 by 200 pixels with 21 spectral channels, while the binary mask has the same spatial dimensions. Instead of using a single pixel as one training sample, I extract a small spatial neighborhood around each pixel. Specifically, for every pixel, a 3 by 3 patch across all 21 spectral bands is extracted, which allows the model to use both spectral information and local spatial context. The code then loops over the region of interest, excluding boundary pixels, and extracts these 3 by 3 by 21 patches, storing them in a NumPy array where each patch represents one training instance. Because boundary pixels are excluded in the image data, the same trimming is applied to the binary mask to maintain consistency, and the trimmed mask is flattened into a one-dimensional label array so that each image patch has a corresponding class label. At this stage, the dataset is split into training and testing sets using a standard train-test split, but before training a model, it is necessary to check the balance between the two classes. By examining the class distribution, it becomes clear that the dataset is imbalanced, with one class occurring more frequently than the other, which could bias the learning process. To address this issue, I balance the dataset by randomly sampling an equal number of samples from both classes, ensuring that sea ice and leads are equally represented. The balanced dataset is then split again into training and testing sets, with approximately 90% used for training and 10% for testing, and a final check confirms that the class distribution in the training data is now balanced. Finally, the balanced training and testing datasets are saved as NumPy files, which will be used in the next step for training and evaluating machine learning models. In this final stage of the assignment, I evaluate the performance of the trained vision transformer model using multiple complementary metrics. After training the model for 10 epochs, I first visualize the learning behavior by plotting the training and validation accuracy and loss curves. From the accuracy curve, we can see that training accuracy increases steadily across epochs, while validation accuracy follows a similar overall trend with some fluctuations, which is expected due to the limited size of the validation set. At the same time, the loss curves show a clear decrease in training loss and relatively low validation loss, indicating that the model is learning effectively without severe overfitting. I then evaluate the trained model on the independent test dataset and obtain a test accuracy of approximately 94%, confirming good generalization performance. To further understand the classification behavior, I compute and display a confusion matrix, which shows how many sea ice and lead samples are correctly and incorrectly classified. Most samples lie along the diagonal of the matrix, meaning that the majority of pixels are classified correctly, while the off-diagonal values represent a smaller number of misclassifications, mainly occurring near class boundaries. This detailed evaluation demonstrates that the model is able to reliably distinguish between sea ice and leads using multispectral OLCI data, and it completes the end-to-end machine learning workflow for this exercise.